Okay, so in 6.1, it's all about looking at general and particular solutions. So when we think of general solutions, that's when we have our plus C. So that's just like when you are integrating something and you get a generic equation. A particular solution is like when you're given a point, and so you have to integrate and then plug the point in and get your actual formula. So for example, if we have y prime equals 2x, we can integrate this and get y equals x squared plus c. The idea being that we don't know what c is. It could have any intercept, so all of these parabolas here would fit this equation. So it's a general solution because it's giving us a bunch of options of what it could be. But if you were given a point, so in this example I gave 2, 5, we could plug that in and solve for c. We have a particular solution which corresponds to just one equation, and that would be your solution given a point. Okay, so this is just a refresher of us being able to get the first and second derivatives as necessary, and then determining if that equation is true or not. So I'm going to work through all three of these. I encourage you to pause and try to finish a problem and then check with me versus just doing it all with me. So we need a second derivative. We already have y, so we're ready to plug that in, but we have to derive this twice to get y double prime. So I'm going to derive it once, and I get cosine. And I derive it twice, and I get negative sine. So if I'm following that pattern there, the second derivative minus the original function, that would be negative sine of x minus my initial y is just sine of x. Those do not cancel out. I have a negative 2 sine of x. That does not equal 0, so it is not a solution of this rule. For b, I can derive this once. My negative 1 coefficient here is going to come down, so I have negative 4 e to the negative x. Remembering that this guy does not change. The derivative of e to the x is e to the x. I just have to take that u prime down to the front. My second derivative, again, the negative 1 is going to come down, and everything else is going to stay, so we're back to positive. And this will keep oscillating back and forth like that as you derive it over and over again. I'm going to pull my formula in, the second derivative for e to the negative x, and I'm subtracting my initial y, which is 4e to the negative x. Those are the exact same, and we have subtraction, so they are canceling out. And so yes, this is a solution to that equation. Lastly, this is a constant, so we know the constant being multiplied is not going to change. E to the x is going to have itself as its derivative the whole time. So our first derivative is ce to the x, and our second derivative is ce to the x, and that would continue so on and so forth. So we do the second derivative minus the first derivative, the function equal to 0. These are the same, it checks out, so yes, it is a solution to that equation. Alright, so given this differential equation here, xy prime minus 3y equals 0, it first wants us to verify that we have a function that qualifies as a solution here, and then also find a particular solution. So the first thing we're going to do is just prove that this equation matches this function. So I'm going to take my function and go ahead and derive it and see what that looks like. So y prime equals, c is just a number, it's some kind of constant we don't know, so it's going to stay. The same way if you had 5x to the third and you would bring the 3 down, that 5 is just going to be multiplied, it's not going to change. We have a similar thing happening here with a c value, even though we don't know what the c is. So the c is going to stay, my 3 comes down, so I have 3c x to the second, it's just my power rule. And then what I can do is go back and look at this equation and say, I have y equals, right here, y is equal to this, and I have y prime equals, that's equal to this, so I'm going to take those two pieces here and plug them in. So that is x times y prime, which I just said was 3c x squared, and I'm subtracting 3 times y. Y for me here is equal to c x to the third. And I am seeing if that is all equal to 0. When I multiply this out, I have a total of 3 x's being multiplied, so I have 3cx to the third, and here I have 3cx to the third. Those are canceling out, so 0 equals 0, so I have verified that it is a solution of that differential equation. For the particular solution, given a point, we're going to go back to our regular formula. This is an easier part actually. We have our function here and we have a point given to us. So I'm going to say 2 equals c times negative 3 to the third. I'm just plugging in my x and my y. So 2 equals c times negative 27. So c equals negative 2 27ths. And therefore, my specific solution is y equals negative 2 over 27 x to the third. So part 1 is right here, part 2 is here. Okay, so with slope fields, you're given some kind of differential equation. For us here, this is our differential equation. And what you're essentially going to do is plug in a variety of points and see at that point what the derivative is. And remembering that the derivative is another way of looking at the change of the function or looking at slope. So by plugging these points in, I can get a y prime at this point, a y prime at this point, and a y prime at this point. And they might all be different values for slope. So plugging my points into here, this is negative 1 minus 1, that's my x minus my y. I get negative 2. Here I have 0 minus 1, which is negative 1. And here I'm getting 1 minus 1, which is 0. So you have these three slopes at their specific points. So you're going to go to these points on your graph and make a little tiny sketch of what that slope is. So I'm going to go to the point negative 1 comma 1, which is like right there. And I'm going to sketch a little baby slope of negative 2. So if you think about rise over run, it'd be going down 2 and over 1, so it's kind of steep and it's going negative. So I'm just doing a little tick mark like that to represent that the slope at this point of whatever this function is going to be tangent to a line that has a slope of negative 2. At 0, 1, my slope is negative 1, so I'm right here. I'm still going negative, but it shouldn't be as steep, so this is going to look something like that. And then at 1 comma 1, I have a slope of 0. So that's a point right here. A slope of 0 is a horizontal line. So that would be my slope field for this problem. Okay, so if you look at the graphs of A, B, and C with me, I'm going to explain to you how I would walk through figuring out which one of these belongs to which graph. So a couple of things to think about here. You want to be comparing some points in between all three of these graphs that have different slopes at those points. So what I mean by that is, if you look at graph A at the point 0 comma 1, it looks like in graph A that is a flat slope. It looks like y prime there equals 0. Whereas in B, if I go to 0 comma 1, there's some kind of positive slope happening there. Maybe it's 1, I'm not sure. But B and C both have a very similar slope here, and it's not 0. So I'm going to figure out which one of these gives me 0, and that's my graph of A. So I'm going to plug in my points here. That's going to be 1 plus 0, which is 1. That doesn't match that, so it can't be I. My x value is 0. That's the only one I'm plugging in here, so y prime equals 0. That's looking really good. I think this is a good contender. And then y prime equals y, which would give me y prime equals 1. So these two guys are giving me a slope of 1 at this value, and this one's giving me a slope of 0. And I can see on my graph at that point at 0 comma 1, I have this flat slope field like that, which is why I know that y prime is 0. Since 2 is the only one that matches that truth, graph A belongs with equation 2. We're going to look at B and C similarly. I'm not going to use this point for B and C because we just plugged it in and saw it, but you can also see it on the graph. The slope is the same on both of these graphs there. They both have a little tick mark like this, which we saw matched because we plugged it into 1 and 3, and they both gave us a slope of 1, and they both have a slope of 1, so it's not going to help us tell them apart. So instead, I'm going to find a different point where I do see different slopes. Sometimes it helps if you have like one positive and one negative, or if you have one that's 0 and one that's a number, something where you can definitely tell it apart. So I'm going to do the point, you can really pick whatever you want. I'm going to pick the point 1 comma negative 1. And the reason why I'm picking that is because I'm looking at B, and at that point, it looks like I have a slope of 0 for B. And for graph C, at that point of 1, -1, I have some kind of negative slope. I don't know what it is, but I know it's negative. So these are going to be different, and hopefully by plugging in my numbers into here, I can confirm which one is which. 2 is taken care of, so we're done there. So we're looking at 1 and 3. So when I plug this point into here, this is going to give me 1 minus 1, which is going to give me 0, which is what I think matches graph B. So that should be I. We can verify this now. I'm going to plug this same point into 3 and make sure it matches what I think is happening over here. So I'm plugging in just the y value, which is -1, which gives me y prime equals -1. That is a negative number, and it doesn't look like it's steeper than that. It looks like it's -1. So C goes with graph 3. So again, you're sort of testing some of these. You're figuring out what the pattern is. You're testing some values. You could have picked other points, but the important thing is you're picking a different point for each A, B, and C. The same point that with different slopes for A, B, and C to compare and see which one of these equations is matching the behavior of the slope on those graphs at that point. They all have a slope of 0 at the origin, so that wouldn't help you. And you can see that if you plug it in. That would give you 0, that would give you 0, that would give you 0. So while it's true, each of these match their graph at the point 0, 0, that's not helping you distinguish which one of these belongs to which graph. Okay, we have a set of points, x and y, and we have a differential equation. We're going to find the slope at all of these points, and then we're going to go ahead and graph our slope field at all of the points that we have up here. So I'm just dropping these numbers into this equation. So here I'm going to have 2 times -2 minus 1. That's going to give me -5. And then I have 2 times -2 plus 1, which is -3, and so on. Try to finish this table now and pause the video. Okay, that's your filled in table with all of your slopes at each of those points. So I'm going to go one by one and go to the point -2, -1. My slope here is -5. It should be very steep and negative. Done. I'm going to go to -2, 1. My slope here is -3, so again it's negative, but it should be a little bit less steep than your -5. I have another -3 slope at -1, -1, so I'm going to try to sort of match what I did there. And so on as you go through all of your slopes. Try to finish out your slope field and let's compare. Alright, here's my final slope field. I've finished out all of those slopes, all of their corresponding places. And now it says use the slope field to sketch the solution that passes through the point 1, 1. So this is a general solution to our derivative equation, which is y prime equals 2x plus y. This is represented here. We have y's and x's over here on the right, so we don't know how to derive that yet, or integrate that. We're not going to do that in this context. So instead of us having to actually solve and plug this in, we know it's going to pass through this point, which means that we know it's going to be going up at that point. And we also know that it's going to follow the rest of the slope pattern. So it's here, as it moves to the right, this is going up and up and up and getting steeper and steeper. So it goes like that. And as we move this way, it's also getting more steep and more negative like that. So it follows some kind of pattern like that. And you're just going based off of this vertical rule of what's happening with all of your slopes. Okay, I know it looks like there's a lot of points on your paper here, but the good news is with this differential equation, it's only depending upon x. So whatever x is, it's going to be the same the whole time. So for example, when x is 0, so all along my y-axis, 2 times 0 is always going to be 0. So my slope field here is going to be horizontal lines all the way through because I'm plugging in x equals 0 for all of those points. It doesn't matter what y is. Similarly, if I go over here to 1, at all of these points, x is 1. 2 times 1 is 2, so I have kind of a steeper positive slope at all of these. When I go over to x equals 2 and plug in 2, 0, 2, 1, 2, 2, all of those, my x value is 2 the whole time, and that's a slope of 4, because that's 2 times 2. So I'm steeper there. And the same thing is going to happen as I move negative. When x is -1, I'll have 2 times -1, and when x is -2, I have 2 times -2. So I'm just going to match these together. I skipped these earlier. And then I'm going to be at -4, so I'm even more steep over there. Now, this is your slope field and it's complete. You could keep going to the left and to the right if you wanted to. This is going to be a slope of 6 and then 8 and so on. And then -6, -8. I'm just plugging in my x values. But what it does say to do is to find the general solution. And so I want you guys to get in the habit now of putting your dx's with your x and your dy's with your y's. We don't have a y in this differential equation, so we are not worrying about that right now. But for now, I'm going to go ahead and multiply both sides by dx to get my dx with my x's. So now I have dy equals 2x dx. And the reason why I've done this is because I want to integrate this to find a solution, and I can't integrate unless I have a dx, and it doesn't belong over here. I'm integrating to find y, and I'm integrating to take this and put it back in terms of x from the original function. So this is going to be y equals x squared plus c, because I'm integrating 2x. And then it says, so that's our general solution right here. And if you can see, which I hope you can, the reason why this slope field matches is because any parabola you're going to draw is going to have this behavior. It's going to have a flat slope wherever its vertex is. It's going to be horizontal. And then the rest of it is going to keep getting steeper and steeper as you move to the left and to the right. So all of these would be a possible solution for this. And that's why your integration matches what your slope field is. It's showing you all the possible solutions. The particular solution has an initial condition f of 0 equals 3. So 0, 3 is a point. When I plug this in to solve for c, I'm going to get y equals x squared plus 3. Because that's my y-intercept. So this is my general solution, and this is my particular solution. And the slope field that matches this is here. If you wanted to graph that specific one, you'd have to go up to the intercept of 3, 1, 2, 3, and say this is your particular solution on that slope field. For the next example, you should be able to do your slope field on your own since we've practiced them together, but I am going to find the general solution with you. So we have dy over dx equals 1 over x. Again, please get in the habit of moving your dx over to the place that has x's. So I'm going to multiply both sides by that and get 1 over x dx. Now that these are together and dy is by itself, I'm going to integrate both sides. Y equals, the integration of 1 over x is ln of x. Plus c. It doesn't give us a specific point to plug in for a particular solution, so this is going to be our general solution. And you'll see on the slope field that you draw, this should be matching a slope field that looks like this, of all these different functions that are ln of x with various y-intercepts. So your slope should be very steep, close to the y-axis, and they're getting flatter and flatter and flatter as you move away from the y-axis. Okay, so wrapping this up, again, I think you guys can do the slope fields on your own here. This one is even easier because this slope is constant. It's always 1. So at every single place on your graph, wherever you are, you're going to have this exact same slope everywhere. All the way through, you have this slope of 1, no matter where you are, on your points. Again, I'm going to put dy on one side and dx on the other. When we integrate this, the derivative of something gave me 1, and that's just x. So this makes sense. We have a line with a slope of 1 that has some kind of y-intercept. We don't know where it is, so all of these lines match my general solution. Then you can plug in your point and get your particular solution. For here, this is where we have a y in place now, so I'm going to put my y with my dy and my x and my dx together. So I'm essentially cross-multiplying, and I have y dy equals -x dx. I can integrate. I actually have a y here now, so I'm going to integrate this the same way I would integrate an x, which is that it came from y to the second, and I'm counteracting that 2 coming down when it derives there. That's equal to -1/2 x squared plus c. And then from here, you can manipulate this a little bit to see a better picture. Don't forget that c is just some kind of constant, so if I want to multiply everything by something, it's not going to change. I mean, it's going to technically change what this is, but this is still just some unknown constant. So I'm going to multiply everything by 2. And then I have y squared equals negative x squared plus, I technically have a new constant now, I have some other kind of constant, but it's still just a number. I'm going to move this to this side, which is x squared plus y squared equals whatever constant I have there. And I hope you can recognize this is the equation of a circle. So your slope field, when you plug it into this for all of your points, should match that. You should be getting these flat points at somewhere, these undefined slopes over there. And then you have these sort of other kind of slopes that are like that. Mine is not perfect, obviously, but if you plug in the values you have, you should be getting these concentric circles that match the slopes of drawing some kind of circle through these, because your general solution is the equation of a circle. And then again, you plug in your specific point and you get a particular solution. I believe that you get x squared plus y squared equals 9, which would be this circle right here with a radius of 3.